Okay, so I'm going to do a little more than what they ask for here. I'm going to figure out every place where the function, we have here the formula for the function, figure out every place where it's increasing and decreasing. That's what the derivative tells me. I'm going to find my local maxes and mins using the first derivative test. Then I'm going to use the second derivative to figure out concavity. So let's start with by taking the derivative. I'm going to get 3x squared minus 12x plus 9. Okay. Our critical value happen when the derivative equals 0 or does not exist. That's a polynomial. It always exists. I don't have to worry about that. I set the derivative equal to 0. So 3x squared minus 12x plus 9 equals 0. I would divide everybody by 3. X squared minus 4x plus 3 equals 0. That factors x minus 3, x minus 1. And I get two critical values, 3 and 1. I'm going to draw a number line over here. 1, 3. This goes on forever. I'm going to do a sign chart for the derivative. So write down all of your factors, and this goes much easier if you write down your factors in the same order that they appear. So I'm going to put the x minus 1 first, then the x minus 3. If you do these right, you get this nice pretty triangle of negatives. Okay, let's draw in all of my boxes here. Okay, now, again, we could just do some test points. If you like using test points, that's fine, but I'm going to show you a shortcut. This guy is going to switch over right here at 1. Let me get my colored pencil out here. Use red. He's going to switch at 1. That's where he equals 0. He's going to be negative every place to the left of 1. Just think about it. Plug in 0. 0 minus 1 is 0. Or 0 minus 1 is negative 1. He's negative below 1, and he's going to switch over to positive after that. Same with this guy. Where is he going to switch? He's going to switch at 3, and he's going to be negative before 3 and positive after. And look, you end up with this nice little pretty of triangle of negatives if you've done this right. And now in each region, we're just going to count our negatives. 2 negatives makes a positive. Switch my color back to positive. In this region, I've got 1 negative. A negative times a positive is a negative. 2 positives makes a positive. That means my graph is increasing on this region, decreasing on this region. Negative derivative is decreasing, positive derivative is increasing. So I'm going to write this out. F is increasing on the intervals negative infinity to 1. We always use parentheses for increasing and decreasing. And then again, so union 3 to infinity. And decreasing on this middle region, 1 to 3. I also notice here, if I'm going up to down, I've got to have myself a local max right here, because the graph goes up and then back down. And I've got to have a local min. I mean, we're kind of sketching out the graph there. The graph's going to do something like this. A local min right there. We'll figure out what those values are when we do a graph. Right now, we're doing rough sketches. If the question said, Joe, a very detailed graph of this function, we'd have to find out what those y values are. But right now, I don't care. Okay, let's do the second derivative. That was just first derivative. First derivative tells you increasing and decreasing. So that was increasing. I'll write these in here. Decreasing and increasing. Second derivative tells you concavity. So I'm going to take the derivative of this guy using this version. That's 6x minus 12. And I'm going to do a sign chart for the second derivative. You're going to be doing so many sign charts over the next couple of weeks. Where does this guy equal 0? 6x minus 12 equals 0. 6x equals 12. X equals 2. This is a possible inflection point. It's not guaranteed. Second derivative equals 0 gives you possible inflection points. These guys have names. Every place the derivative equals 0 or does not exist, we call a critical value. Write that down. Critical values, derivative equals 0 or does not exist. When you set the second derivative equal to 0, you get possible inflection points, but it's not guaranteed. And as far as I know, nobody ever gave these things names. Like we don't call them like second critical values or something. It's possible nothing interesting happens there at all. So I'm just going to write here, this is a possible inflection point. And I think in this case, it will be 1. Okay, so we draw 2 is my possible inflection point. Now I'm checking his sign. All I care about is positives and negatives. Check his sign. So F double prime at anything smaller than 2, say 1, would be 6 minus 12. That would be negative 6. That's a negative. And over here in this region, pick any number over here, F double prime at, say, 3. That would be 18 minus 12. I don't care what it is. It's 6. It's positive. Negative means concave down. Positive means concave up. I just switched from concave down to concave up. I do, in fact, have myself an inflection point right here at 2. So I could write out the graph, because this is the stuff the question actually asked for. It didn't ask for that. It asked for the function is concave down on the interval negative infinity to 2 and concave up on the interval 2 to infinity. We have an inflection point. I'll write it out. At 2, comma, now we need to figure out what the actual, this one, because it asked for it. List all inflection points. Inflection points are points, not numbers. Points have an X and a Y. And we've got to plug back into the original to find that. Again, the question didn't ask for the local max and min. If it did, I would have to plug these values back in and find that local max and min on the original. The question does ask for my inflection points, so I got to plug that back in. F of 2, and that's original. So F of 2 would be 2 cubed minus 6 plus 9 minus 6 times 2 squared plus 9 times 2 plus 30, whatever that is. I don't know if you need to watch me. I'm just going to dot, 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 dot. Okay, so now we could do a rough sketch of F. Just based on everything we found. Once we do a couple more examples, we'll be drawing a very detailed graph. I won't use the word sketch, I'll use the word graph. Here, I'm just going to do a quick sketch. I know the graph is increasing until 1, decreasing between 1 and 3, and then increasing again. So 1, 2, and 3, this is where all the interesting stuff happened. So it was increasing until 1, decreasing between 1 and 3, and then increasing again. So I had a local max. Same thing I wrote above. Right there. Here's a local min. Again, if we were drawing a graph, we would be finding all the x-intercepts. I don't know if there's an x-intercept at 2 or right there or right there. We would find those. We would find the y-intercept. We would find the y value at this local max and min. We would find, I don't know, like whatever that number is, it's probably not there. But that's where I'm trying to switch from concave down to concave up. So that, I just happened to put it there on the x-axis. It should be at whatever that value is. That's why this was just a rough sketch. Okay, that's a good place to stop. And now we'll do at least one full example.